All right, welcome back. So now we're going to look at determining the inverse of a matrix. So let's look at this example here as a way to introduce this. Okay, so we have this matrix and we want to find this matrix, but we don't know what it is. So how are we going to do this? So let's do it this way. Let's say we have, well, what do we know? We know that A times A inverse equals this. It has to, right? If it exists, right? Then we know that it has to equal the identity when we multiply them this way, or the other way, and the other way, I should say. Okay? So, let's set it up by just taking a generic value of this, right? So let's say we have 2, 9, 1, 5. And let's just take a generic matrix, A, B, C, D is equal to 1, 0, 0, 1, right? So now let's multiply this out. And so what do we get? We get 2 times A plus 9 times C, and then we get 2 times B plus 9 times D, and then we get A plus 5C, and then we get B plus 5D, right? So we get this matrix right here, okay, with our 4 entries, 2 by 2 matrix, and each of the elements is represented by these expressions, and then that's going to equal 1, 0, 0, 1. Okay. Now notice something here, that we end up with 4 equations, right? We end up with this is equal to this is equal to this is equal to this, and this is equal to this. Also notice that this matrix is repeated right here and right here if you look at the coefficients. 2, 9, 1, 5, 2, 9, 1, 5. So this is equal to this column, right? These two are equal to this column, and these two are equal to this column. So what we end up with is, let me write out the equations first. So we get 2A plus 9C is equal to 1. And we get 2B plus 9D is equal to 0. We get A plus 5C is equal to 0, and we get B plus 5C is equal to 1. Okay? Now, what we can do is, since these are repeated, right, for each of these columns, what we can do is we can write an augmented matrix using just this coefficient matrix here and this matrix here. So before we do that, let me look at this. So we've got 4 equations with 4 unknowns. And so what happens if we solve this, right? So we've got 4 equations with 4 unknowns. And so how would we normally do this if we were setting up the matrix, right? We would have A, B, C, D. Right, so we would end up with 1, 0, 1, 0, 1. We would end up with 0, 1, 0, 1, 0. We would end up with 1, 0, 5, 0, 0, and we would end up with 0, 1, oh, hold on. Did I write that right? Well, A 9C equals 1, 2B 9D equals 0, A plus 5C equals 0, B plus 5D, oh, plus 5D plus 5D. So that would be 0, 5, 1. And we would just solve this, right? By getting this by setting this up in either reduced echelon form, right? Or echelon form. Okay, and so we could set up 2 equations, right? But we could also set up these 2 as separate equations for A and C, right? 2 equations with 2 unknowns, and we could set these 2 up as 2 equations with 2 unknowns, right? And so that's where I come back to here. Here we've got 2 equations with 2 unknowns related to this column. We've got 2 equations with 2 unknowns related to this column. And so we could actually split this up where we can have the same matrix. So what we can do is we can set this up as an augmented matrix with just this and this. So we can set it up this way. 2, 9, 1, 5, 1, 0, 0, 1. And so now what it turns out is we can use the elementary row operations on this one, and it would solve the same system as if we had the larger one that we would normally set up if we had 4 equations with 4 unknowns. Okay? And so in this case here, what we would do is we would use the elementary row operations. And so let me do that right now. And so let's say the first thing is what we want to do is we want to do the elementary row operations so that what? So we can get this in reduced row echelon form, right? Where we have a diagonal of 1s, right, along the Mine diagonal, and 0s everywhere. In other words, we want the identity matrix here. And then what happens is this will tell us the inverse, because the inverse will be here. So we start with A and the identity, and then when we're all done with our elementary row operations, we will have the identity here, and then whatever is over here will be our inverse matrix. So let's do that. Okay? So the first thing I'm going to do is swap these rows. So I'm going to go row 1 with swap with row 2. And so that's going to give me 1, 5, 0, 1, 2, 9, 1, 0. And then now what I'm going to do is I'm going to eliminate the 2. So I'm going to do -2 row 1 plus row 2. And I'm going to replace row 2. Okay? And so that's going to give me now what? Now I'm going to get, the first row stays the same, so it's going to be 1, 5, 0, 1. And the second row is now going to be what? 0. And then -10 plus 9 is -1. And then 0 plus 1, this is going to be unchanged because -2 times 0 is still 0 plus 1 is 1. And then -2 times 1 is -2 plus 0 is -2. Okay? All right, now I'm going to multiply the second row by -1. So I'm going to take row 2 and replace row 2. And so that's going to give me 1, 5, 0, 1. And this is going to give me 0, 1, -1, 2. Okay? Now I'm just going to eliminate the 5. So I'm going to take what? I'm going to take -5 row 2. So -5 times row 2 plus row 1. And I'm going to replace row 1. And so now I get what? I get 1, 0. And then -5 times -1 is 5, plus 0 is 5. And then I get -5 times 2 is 10, or -10, plus 1 is -9. So I get -9 up here, and then the second row stays the same, so that's going to be 0, 1, -1, 2. And now I'm finished because now what I've done is I've row reduced this as much as I can and I've got the identity. That means that A inverse is equal to 5, -9, oops, -1, 2. And that's it. And that is how you find the inverse of a matrix if the inverse exists.